Okay guys, in this video lesson we're going to take a look at reaction spontaneity and how we can use enthalpy. Remember, enthalpy, changes in heat, and entropy are changes in disorder, and determine if a reaction is spontaneous or not. Okay, so here we go. Now when you compare the two things in terms of enthalpy and entropy, remember enthalpy is heat, entropy is disorder. Okay, so changes in enthalpy. If we have a positive change in enthalpy, it's endothermic. If we have a negative change in enthalpy, it's exothermic. Okay. Remember, enthalpy, reactions that release energy is delta H is negative. They tend to be spontaneous. Okay. So you want to have a negative enthalpy change. For entropy, and your changes there, a positive means more disorder, a negative means less disorder. So it's actually opposite of enthalpy. So regarding entropy, if you want a reaction that becomes more disordered, it'll be spontaneous. So the perfect combination is exothermic and more disorder. So negative here, positive here. That's our perfect combination. Okay, so now what we're going to do is take a look at this through an example, okay? So here we have baking soda and sulfuric acid, and we're going to react them together. Okay. Now this is a spontaneous reaction. So if I put baking soda with sulfuric acid, it's going to fizz, it's going to foam, it's going to make carbon dioxide, very much like the old volcano reactions that you did in middle school. Okay. If we were to measure the temperature change while this runs, this actually is an endothermic reaction. Okay. So if that's true, what must be true about entropy? Okay, so endothermic says that the reaction won't be spontaneous, so that must mean that entropy is telling it that it will be spontaneous. So the entropy here must be positive. Okay, we must have a positive entropy. In fact, it has to be more positive than the endothermic, so it overrides it. All right. Now we're going to take a look at the math and break this thing down. We want to take a look at our net ionic equation for this because it simplifies it and makes us do less math. Okay, so we have our hydrogen ions reacting with baking soda or sodium bicarbonate. It's going to make some sodium ions, some carbon dioxide, that's the fizzing we see, and some water. Okay, so 1 to 1 to 1 to 1 ratio, which is kind of nice. So here is your value. So here is your standard entropy changes. Here is your standard enthalpy changes of formation. So what we want to do is use these numbers and let's solve for what is the delta S for the reaction and what is the delta H for the reaction. That way we have some numbers to compare to. Okay, so go ahead and do that now and pause the video, and then we'll take a look at it here in a second. Okay, so assume that we paused it and we worked it out. So if we did that, what we should find is that when we did the entropy change to the reaction, we take all of our products, and since it's all 1 mole, we'll take them all times 1 times 1 times 1, minus our reactant, and we get a change in entropy of 240.56 joules per Kelvin. We do the same thing for our enthalpy, and we get all your products, add them up, so these are all negatives, so it's a negative plus a negative plus a negative, minus another negative, and we get a change in 31.8 kilojoules. All right, so let's take a look. Entropy is positive, should be spontaneous. Enthalpy is positive, it should be non-spontaneous. Okay, so the entropy here has to override this. But if you look close, this is in joules per Kelvin. This is in kilojoules. Okay, so if you look, we only have 240.56 joules per Kelvin. Here, if we convert this, this would be 31,800 joules. Okay, so there has to be something else here. There has to be a reason why 240 joules can dominate over 31,000 or 32,000 joules. Okay, if we compare these numbers at the same units. Now the trick here is this K. Okay, this is joules per Kelvin. So this value is related to the energy times whatever we have in kelvins, or basically our energy per Kelvin. So if we are running at room temperature, we're running at 293 kelvins. So really, to compare joules to joules, we have to multiply this value times the temperature to get an idea of how much entropy really plays a role here. Because remember, entropy is temperature dependent, so we need to factor that in. Now, if we do that, we're going to get an equation here in a minute. But before we get to that equation, let's just make sure we have our table down in terms of what we're talking about. So if you have enthalpy positive, entropy positive. Will it be spontaneous? Well, that's temperature dependent. We need to look at that. The higher the temperature, more likely to be spontaneous, because if the more temperature we have, and we're going to multiply that by entropy, it's going to make this dominate. If you have a plus minus, it's always non-spontaneous. It's always endothermic. It's always getting more organized. If it's minus minus, lower temperatures make it spontaneous, because we want to multiply the entropy by a small number, so then this would dominate, making it spontaneous. And then, of course, the minus plus, where it's exothermic and becomes more disorganized, is always spontaneous. Okay? So let's now take a look at this equation we can use to solve for this. So the equation that we use is called Gibbs free energy. Okay? And we're actually solving for Gibbs free energy and the change of that. Now, this equation that we see here, it's going to be a delta G. If you notice, like we talked about before, we have our enthalpy being compared to our entropy. So it's going to be enthalpy minus, because they have opposite sign in their effect, the entropy change times temperature. Okay? So like we talked about earlier, that for us to figure out if a reaction is going to be spontaneous overall or not, we compare enthalpy to entropy, but we have to multiply the entropy by temperature, and we need to have them in the same units. Okay? Now, to do that, we solve for the variable called Gibbs free energy. Keep in mind, temperature must be in kelvins, and that when you work with delta H and delta S, they both should be in kilojoules as you work with them also. Okay? We're going to stop the video here, and in our next segment, we're going to go deeper into how to use this equation and to work through Gibbs free energy. Thank you.